I designed this bracket for an aircraft, and within a couple of years it had already failed. So in this video, I'm going to walk you through what caused the failure and what 3 things I did to fix this to prevent it from happening again. Welcome back to Engineering Aerospace with me, Eric Kane. Now, obviously every engineer doesn't like to see their designs fail, but this is one of the fastest ways you can learn lessons that you may not have picked up prior. And so I wanted to use this opportunity to talk through one particular scenario where a component that I designed failed, what lessons I learned, and how you can go about improving the designs from the lessons of others so that you don't have to make these same mistakes. Now, I want to give you a little background and context, so I'd like to kind of draw out kind of what the particular situation was for this design. So we're designing an equipment installation that was hanging underneath an aircraft, and so I had to work with existing airframe structures and design a support platform that tied into the aircraft structure to hold this equipment. Now, it's in a situation where the components have to come in and out with some regularity. It's not constant, but it is something that occasionally happens. So it needed to be easily installed and removed from the aircraft, so it couldn't be a permanent installation. And the basic design that we had come up with was effectively something like this. We had a large plate that mounted the equipment, and we'll just say it's just some sort of box here. And then on either side, on the back, we had a pair of brackets, and on the front we had another pair of brackets. Now, these brackets were intended to basically be a lug and clevis kind of configuration where we would run a bolt through these two in the front, and then we'd run a bolt going 90 degrees through the other two in the back. And so if you looked at this from a side perspective, you might have a plate like this, and what we had was brackets, for example, on the top, and you would run a bolt through the aft brackets this way, and of course running kind of in and out of the page in this orientation for the other brackets. So, and then of course your equipment was mounted underneath. Now, what we were using was effectively, like I said, a lug and clevis design. Now, a very basic one would look something like this, where you have a simple lug and a clevis, right? And these two sides would be potentially bolted or riveted or something to another section. And the main transfer of load is through a bolt, a shear bolt, that takes the shear loads through one or both of these legs of the clevis, and it can go either direction. But that's the basis of the design, the advantage being that you can easily install and remove these bolts and get the whole assembly off the aircraft. So let's go to SolidWorks, where I've kind of mocked up the design of this assembly. I've left off the fasteners that tie to the nearby structures, but this is really the joint of interest here. And so you can see I have this, in this case, this is basically a finger joint where it's multiple, kind of a multi-clevis design. And that was partly just to help take some bending moment out of this, but realistically those forward attach points should be taking the 4 aft loads, and then the aft attach points should be taking the side-to-side loads. So in this case, this is actually the aft attachment setup, and we had a bolt of some sort, and I don't remember all the details in this case. This was a while ago, but and I couldn't even probably talk about all the details anyway, but this is basically like a number 10 or a 1/4 inch diameter bolt that we used, a fairly long one to get through this length of material, so you're having a very long skinny bolt. And then it was attached with a nut on the far side, and so if I kind of explode the joint assembly here, you can kind of make out how these components come together. So the bolt obviously goes through both of these components and then gets bolted, tightened down with the nut on the other side. So this assembly worked for a while, But then we got notice from some of our maintainers in the field that one of these brackets had broken. In fact, one of these legs, one of these clevises, had actually just snapped off in one of the operator's hands. So they were going to do some maintenance and pulled some equipment off, and then just happened to break this piece off. Now, this is a thick piece of 2024 T3 aluminum. So, it should be a fairly rigid, strong material. So the fact that he was able to break it off by hand tells you that a lot of damage had already occurred. And so the component was sent out to a lab to analyze it, and they determined that there was corrosion damage that caused this. It wasn't necessarily a fatigue problem, it was a corrosion problem. Now, if you know anything about 2024 aluminum, is that it's very susceptible to stress corrosion cracking. It is a weak resistance to corrosion. And so even though it's really beneficial in the aerospace world, particularly the aviation world, where it has a very good fatigue resistance and a very high strength to weight ratio, the problem is it's very corrosive, susceptible. And so it doesn't take very much of an impact to the coating materials for this to cause a problem. And so these materials were coated with just a chem film coating, so allowed for electrical conductivity while providing some level of corrosion resistance. However, as I mentioned, this particular assembly was designed to come in and out. So there was some chance that technicians working on this could bang into it with wrenches, or as they're moving the installation in and out, could ding and scratch the surface on this material. And any exposure of the underlying aluminum to the outside environment could allow it access for corrosion. The other problem, and the reason that this particular one failed, was because it was being operated in a corrosive environment. It was near the ocean at its field base, and so that basically suscepted the aircraft to salt corrosion. And so the likelihood is that this component saw a much faster corrosion environment than if it were operating in a dry location like Arizona or something. And so it's probably why it was the first one to fail. And of course, as soon as it failed, we had to go inspect the entire fleet, right, to go make sure that other components were about to fall or break off in flight. Fortunately, this occurred on the ground when it was identified, didn't cause an incident in the air. And so we had some time to go investigate. Now, you can look at this design. It was plenty strong based on the initial design properties for the loads that it was subjected to. Arguably, probably had more mass than it was necessary. The bolt was sufficiently strong, but what had happened is near the base of this component, you can see where this radius is. It had basically cracked all the way through. And so normally we add a radius to help minimize stress concentrations, particularly in the aircraft world. This reduces the likelihood that you're going to get some sort of fatigue cracks and that kind of thing starting. And so, at first this might seem like a reasonable design, but if we open up the actual bracket and kind of look at it in more detail, it can kind of show you where the problem is. So I'm just going to open it here in SolidWorks so we can look just at this bracket. So as I mentioned, it was basically this component here, and it had sheared almost right about here where it attaches to the main plate. Now, at first you might not realize it, but this is a very sharp edge, right? Even though we've radiused this, like when I look at it from the side, it's kind of got a sharp 90-degree corner here, right? Transitioning. And so that has potential to be a stress concentration point. And it's very easy for a very minor scratch or something to dig into the material there and break through the surface finish and be an initiation point for corrosion. So that's likely where everything started, and then basically it corroded through the whole bracket to the point where it just fell off. So what could have caused this? Well, as I mentioned, the material was probably less than ideal. If we had used something like a 6061, it's much more corrosion resistant. but it's a little weaker material, and so we may have needed to use more mass to accommodate that, the geometry necessary to accept the loads. But in the end, we decided to just change this bracket to a stainless steel fitting. Now, stainless steel is great in terms of its corrosion resistance in a saltwater environment like that. But there are a couple trade-offs, right? Steel is much heavier. If we didn't change the geometry because we wanted it to remain the same basic interface and reduce the time to make a fix. But that means that's adding weight. Now, these aren't huge brackets for the size of the aircraft, but it does add some mass to the installation. So you can change the material to, say, a 300 series stainless, and that has benefits of avoiding the corrosion issue. But it does add weight, and so that's a factor. Now, just replacing one piece of aluminum for a piece of stainless isn't always just as simple as that, right? Because now we have dissimilar metals, right? This is being mounted to an aluminum airframe. And so if we are going to use a stainless steel against aluminum, we may have to provide some additional corrosion barrier between those, because otherwise you're going to get a galvanic corrosion potential. And so to avoid damaging the airframe structure, we would have to insulate the two materials from each other. That may be done with a sealant, right? There are a variety of sealants available for aircraft applications that can be applied wet, kind of like an epoxy, but a little more flexible and soft. And then you can join the two components. And that provides an electrical barrier between them. Now, as I mentioned, the components here are actually electrical in nature, and we wanted to have a ground path, an electrical bond path back to the airframe. And so the original joint was kind of used as that bond path. Now, it's not the most ideal because of all these different joints going through here, but an alternative to that would be just to run a ground strap, right? So I can switch back and show you what that might look like. So in this case, we had a bracket here hanging below, say the aircraft is up here. So rather than relying on the basic structure that is mounted to the airframe to provide an electrical bond path, what you can do is you can basically provide a bond strap, right? And so depending on where the structures are and how all this lines up, you would have basically a braided copper nickel strap, and that could provide an electrical conductive path. Now you would need some sort of fastener usually to attach these on either end, but it can be basically a flexible bond strap. It adds an extra step for the install removal of this equipment, but it provides that electrical bond path if you have to insulate, for example, between two materials here, and that can no longer be a structural bond path. So let's go back to the bracket real quick and kind of look at some other things that we could do. So besides just changing the material, one of the things you might look at again is this particularly sharp edge here, right? So we could minimize the potential for stress concentrations in there, right? And so I looked at what could we do to change the radius here, right? So we have one fillet in this kind of corner in this direction, and that prevents it from having a stress concentration along the axis of the bolt. But that's not the primary loading axis, right? Vertically and horizontally is where the loads are intended to go. So, right here we've kind of got a sharp corner. It's not as bad because it's almost at a 45-degree angle, so the stress concentration is not as bad. But one thing you could do is you could come in and add another fillet there. Depending, and I've got this model just in metric just for illustration purposes, but you can see that the fillet's a little bit awkward in this location, right? So I can't make it 22, but if I can make this a bigger fillet radius, you can kind of start to see there's some weird geometry going on because this extends out to the edge of the bracket, and you don't really care about that out here. And it's just a little odd. Now, another approach you might take, instead of trying to fillet this edge is to just directly on that sharp corner. And that's better, but you can see again, now you've got some weird geometry that goes on with this feature, right? So we've still got a bit of a kink here. Now in order to carry this through, we either have to extend it all the way around all the tangent edges, or we have to start doing a variable radius fillet, and that starts to get more complicated. I mean, it can be done. You can come in here and mess with the geometry using surface features and such, but this gets really complicated really quick. And so it's ideally something we would avoid having to mess with. Now, because of the particular brackets we were working with, they were fairly limited in the number of quantities. And so we just basically asked the manufacturers put it on the drawing to blend this corner out. So rather than filleting the whole thing, we just basically put a note in here to say smooth this corner off, right? To blend it out such that it is not a sharp corner, and that'll reduce the stress concentrations. But honestly, you know, there's only so much you can do with that particular bracket design. You could rearrange this to make the geometry work better, but it really wasn't necessary. We just needed to avoid starting a corrosion point here, and so we just kind of helped blend that out. But the real cause of this whole mess was, if I go back to the assembly, was really the bolted setup we used here. Now, as I mentioned before, you go back to the tablet design, really I have existing 4 attach points, right? So I have these 2 on the back and the 2 on the front. And of course, the 2 up on the front are designed to take these 4 aft loads, and the 2 in the back are really designed to take the side-to-side loads. So now all 4 of them are kind of sharing the vertical load, right? So in this case, I have vertical loads on these views. But really, we only have to take load side to side and vertically in this bracket. So the 4 aft loads should not be something that is a main driver for the design of this bracket. And so why did it crack that way when we were basically cracking on what is effectively a bending of this face? Well, basically pushing in and out from the bolt direction, right? And so this was because of the clamp force. So there's a nut on the back side of this assembly, and when those were designed, we put on a typical bolt tolerance or bolt torque requirement, right? So typically when you tighten a bolt, you're going to be tightening it somewhere to 60 to 80% of the tensile load of the bolt. Now, in this case, we're actually using the bolt more as a pin, not as a tension fastener. And so that type of tension on this assembly was not necessary. All it was doing was causing a bending moment on these 2 outer legs of the assembly, trying to squeeze them together. And so that was creating a stress on these outboard faces here. And so that stress is what caused basically a stress corrosion crack to occur. You had a continuous load in a corrosive environment with a material that was not well suited for that. And so that caused this bracket to fail very rapidly. So what could we do differently? Well, because the 4 aft brackets are taking the load in the direction of the axis of this bolt, I don't need any tension on that bolt. In fact, what I could do is I could literally just put a pin that is captive in here, right? Put a couple retaining rings on a pin, and that would actually keep the pin in place. It's not really taking any load down the axial direction of the bolt. And so I don't need to provide that clamp, that compression into the 2 legs of this bracket. So what we did is we actually designed this so that this was only finger tight, and you had a locking feature that was designed to secure that in place. But you could easily replace this with like a cotter pin and like a straight pin with a cotter pin on the end or something like that. So if you have ever used like a trailer or something on a pickup truck, that's the same kind of thing you a lot of times see. Just a pin goes through and you put a little cotter pin on the other side to keep it from coming out, and it can take all that shear load. So that would have avoided this whole issue. And so those are the 3 things that we did to repair this assembly, was to change the material, reduce the stress concentrations and change the callouts for the tightening of the assembly to not use basically a tension torque on the bolt and relieve that stress that was on the part. So I hope that was useful for you. That's just one example of many mistakes I've made throughout my career. If you're interested in learning more, please reach out. I'm going to be having some new announcements coming up soon on some new things I'll be doing for young engineers. So until next time, see you then.